My name is Sarah Penniston-Dorland. I'm from the University of Maryland, and I'm pleased to be able to moderate the next session, which is a second golden age for metamorphic petrology. The session was proposed by a graduate student named Carl Hoyland, who's at Stanford University. And Carl had the perspective to recognize that metamorphic petrology experienced a golden age. I guess he's giving it the first golden age, with the advent of the electron microprobe and the use of equilibrium thermodynamics to understand pressure and temperature conditions and apply those to crustal problems and understanding how the Earth behaves. He also has the perspective to understand that we are perhaps now entering a second golden age of metamorphic petrology, with our ability to measure things on ever smaller scales and to measure very small concentrations, abilities that we haven't had previously, and to use processes other than equilibrium. So thinking about processes such as disequilibrium processes, thinking about chemical disequilibrium, but also recent developments in metamorphic petrology are allowing us to understand or to use and interpret mechanical responses of minerals and rocks in order to try to, again, make sense of crustal processes and the Earth. So our two speakers today are designed to shed some light on some of those new directions that metamorphic petrology is taking to get us to think about these ideas, to think about the future of metamorphic petrology. So our two speakers are Ross Angel, who's going to be talking about physics and thermobarometry. He's from the University of Pavia. And then also Lucie Tajcmanova, who is from Heidelberg University, who's talking about exploring the future of metamorphic geology.
What is the future of the field of metamorphic geology? This has been a question which I asked also several times during my career, so it's really my pleasure to get this opportunity to discuss this during this event, and thank you all the organizers for making this event happen. So since Ross showed his team from Pavia, I also show you or not my team, obviously, because this comes, this is a little bit older. It's from 1895. It's a picture from Heidelberg, and I just realized, because I'm new there, and I just realized that there was a big interaction between Heidelberg and US scientists. This is full of US scientists, and what I like on this picture, because they actually, I have to say why they came there, because the first modern petrographic microscope was actually invented there. And I like this picture from several reasons, because those guys, they study things like the basic observations. They try to understand the processes in rocks, or to explain their observations with basic physics. It means that they did basic research, and I use this basic research several times because nowadays it has a kind of meaning of redundancy, or sense of redundancy. But I will repeat it several times during my talk because I think it's still important. So why actually my title is called, or has metamorphic geology and not petrology in the title? Because when we look at all these processes like mountain building, earthquakes, volcanic eruptions, geothermal energy ore deposits, there is always metamorphism or metamorphic processes. Now I'm turned off probably, yes. Metamorphic processes behind. And it's never only the chemical process, it's always a coupled chemomechanical process. It means that the mineral reactions or fluid flow is always linked with deformation, and it doesn't have to be large scale like mountain buildings, building, but it also can be on the small scale. Like if we have a fluid flow, it can be on pore level. So, and I will explore the future of metamorphic geology from the perspective of these 3 points: research, education, and visibility and bigger picture application. I could not help myself to check what happened during the last 100 years when I was preparing my talk. And I don't want to give you the historical overview, detailed historical overview on what has happened. I just choose certain milestones or points or events where I think that they are important, that they influence our current stage of metamorphic geology as it is now, and also that they might have an influence in future. And when we go back, so at the beginning, it started with Goldschmidt, who practically set up the basis for modern thermodynamics and thermobarometry, which was then continued mostly, like the most significant were J.B. Thomson and Korzinski on the other side of the world. Then we started to have experiments, and the thermobarometry was invented. And together with experiments, we go towards also that the first thermodynamic databases were put together. And then also the application, as already Sarah said, the application of electron microprobe brought the observational part into completely different level. And then, of course, we went towards higher and higher resolution to the TEM. And also, when I go to the bigger picture, I should not forget plate tectonics, discovery of plate tectonics. And what all these things, all these milestones, they have in common is that the people invested time to basic physics and detailed and careful observations. The last couple of decades, the effort was spent to develop the tools for phase equilibrium modeling and solution models, which is very detailed, time-consuming, and very appreciated effort because we practically got tools and which improved our automated quantification of the observations. And all these things, they paved the way for us. So where are we now? The advances in computational and or the technical and computational advances, as well as the analytical advances, they grow exponentially. Nowadays, we can do the field mapping with drones. We can calculate complex diagrams. We can use numerical models. When it comes to analytical advances, we can practically study the rock microstructures in 3D down to the nanometer scale. So this is really impressive. Like looking back 100 years where we had a horse in the field and some sketches, we can use drones and so on. So everything is very impressive. But all these advances are practically due to advances in other fields, in computer sciences, physics, engineering. And we still have to figure out what is the research question in geosciences. It means a research problem which would take into account the observations, basic physics, chemistry, math, and critical thinking. So where are we today? So today, the metamorphic geology, the role of metamorphic geology is to provide PT estimates for geodynamic reconstructions. And I check the recent journals, recent publications, and good 80% of the current metamorphic studies are practically dedicated to provide PT estimates for a certain region for the geodynamic reconstruction of certain region, which is not bad. I mean, it's important. We need those data, and I did them in the past, and my master students, they regularly do them as well. But the point which I want to make here is that all these studies, they practically apply established methods. They apply state-of-the-art analytical techniques. They apply state-of-the-art quantification tools. And sometimes the users are not even forced to know the background of the tool, like the quantification tool. They use it as a black box. So this this practically put me into our thinking and asking the question, does this really guarantee us progress and independence of the field in future? Because, or put it other way around, can the estimating PT conditions satisfy us for the next 100 years? So if I summarize, or if I look at it in a bit in a detail, and I summarize what I just said, that 80% of the studies, what we see there is that we increase the automated quantification. We have super precise analytical data. We are also forced to publish super fast. But on the other hand, we are losing really the physics-based interpretations. Since we are forced to publish fast, it's questionable whether we have careful observations and also critical thinking. And my question is, aren't we losing independence in our research? Because on the other hand, we have still open questions. And these open questions are not like something fancy, they are really basic questions. Because when we open the textbook of Metamorphic Petrology, we learn in the first chapter that there are agents of metamorphism. They can be temperature, pressure, and I put composition and fluids together. And there are still open basic questions related to those agents. We still don't know what's the source of heat for metamorphism in certain regions. We still don't know what is the role of pressure and stress on equilibrium, or there is a big discussion how to implement them in thermodynamics. And we still don't know what is or how the metasomatism works even on the small scale. So, and if we use the applied thermobarometry, it doesn't help us to explain these basic but very important questions. And I don't say that there is no one studying that. There is this 20% of publications which are dedicated to better understand these open questions. But we need more. We need more of these physics-based studies to understand the processes. And I actually like this quote from 2000, and I think it's still relevant, that our ability to interpret natural compositional variability is far worse than our ability to measure it. And it's mentioned for the compositional part, but it can be practically valid for all the agents of metamorphism. Good. So then I did a little bit of research, and I found a document with 10 questions shaping 21st century earth science. And one of them, surprisingly, it was not everything about climate. One of them is how are earth processes controlled by material properties? So, wow, it's cool, because petrology is actually material science of the earth. And then there are these big global statements that understanding the processes on the microscale can help us to understand how the planet Earth works and also the other planets. Good. That always sounds like Bruce Willis saving the world. But it's true, because when we look at something really global, which is plate tectonics, surprise, surprise, after 50 years, we are not still able to explain self-consistently the initiation of the subduction. We have 14 hypotheses that have been proposed to explain this process self-consistently or physics-based. So it means that maybe this is the way where we can focus on our open questions, like for instance, the open questions related to the pressure and to the heat for the metamorphism, to somehow contribute to this or to remove this controversy. And it doesn't have to be this document about 10 questions for the whole earth sciences, but I went to the literature which is really focused on this geodynamics and the problems with the mantle convection and how to initiate the subductions and so on. And it's from 2017, and they cry for getting more data on experimental and observational, direct observation basis. So it means that they need coherent physics-based description of material properties from grain scale. Isn't it wonderful? We have a space where we can practically help to contribute, or we can help to understand even global scale processes. So to have a look at some specific examples how to deal with these open questions, I will show you an example what my research group has done last couple of years, where we played with this pressure metamorphic agent, we were interested in implementing more mechanics into our petrological quantifications. And we focus on so-called the mechanically controlled microstructures, which are microstructures where if you put a material, like minerals, with different material properties, you deform them, which can happen during the metamorphism. And it means that the stress and pressure distribution, stress and pressure variations can be developed during this deformation. The simplest example of such a mechanically controlled environment is inclusion host system, which Ross already introduced. And the important thing is that those microstructures are practically, they preserve information about stress state in the lithosphere. And if we are able to recover it, it would be a good source of data for those geodynamic people working on the plate tectonics. But what I want to also say here that it's not only the stress and pressure variation which is developed, but it has an effect on chemical redistribution. This pressure variation or stress variation leads to the redistribution or specific redistribution of material. It means that compared to the classical chemical view of rocks, where we have a chemical zoning, we can also have a chemical zoning which is a result of pressure variation across the grain if we have a solid solution. And as I said, our group spent some time on developing tools to quantify such a system, such a microstructures. And for instance, we took mechanically controlled microstructure where this is an example of plagioclase grain, which is zoned. This is the anorthite component. And we are able to calculate the pressure profile across the grain. Nowadays, we are able to even measure, so this is the same grain and HR, high angular EBSD method, which is freshly introduced to geosciences. This is like really rough picture because we are still investigating the limitations and capabilities of this method on geomaterials, but already now I can say that this, for instance, in this example, the effective stress across the grain is 6 kilobar, and it's like 100 microns. The other thing which was of our interest was how the mechanics can influence the diffusion, the chemical diffusion. So our student Xin Zhong, he coupled chemical diffusion with intracrystalline deformation. So let's look at this specific example, where on the left side we have practical chemical zoning, if that works. This is like a grain, this is like a Gaussian curve, like as if we had like an anorthite component, high anorthite and low anorthite here. On the right side, we have a pressure profile, and the initial stage is practically as if we assume from the classical point of view, it's a flat pressure profile across the grain. So now we let it diffuse, so the diffusion starts and the reequilibration starts. So from this initial profile, we get down. This is flattening of the diffusion, and due to the different sizes of the components inside a grain, what happens with the pressure, it jumps. So this blue line here corresponds to this jump here. The second, the red line is even higher pressure jump, the second step of the reequilibration, and then it both they relax. But it significantly slows down the diffusion compared to only chemically based diffusion. So this, our research opened several questions, like how does mechanics influence our current quantification approaches? What do we really know about chemical diffusion? It means, for instance, the diffusion coefficients which we have now, are they satisfactory? I would suggest we need new kinds of diffusion experiments which take into account the chemomechanical coupling. And it's not only these specific things which my group has done, but the mechanics can influence other parts of other petrological features. And I just chose these two, which are practically two major points which I found in the current literature, like what are the hot topics. And let's look at the disequilibrium and implementing kinetics. This has been long discussion all the time, but what is practical kinetics is the departure from equilibrium. And if we evaluate our equilibrium only in the classical way, it means that assuming no pressure and stress variations, and then we implement the kinetic theory, and we don't explore equilibrium with stress and pressure variations, we might have overlooked some important features there. The other thing is this Raman barometry, and Ross has spent already some time speaking about that. So there are certainly uncertainties, and it means that Raman barometry is not that innocent. It means that we cannot say, I will stop using phase equilibrium modeling because I can just shoot my inclusion and I get a pressure. Because it's not that simple. And from mechanic point of view, I would just add to what Ross mentioned, I would add there is always viscous relaxation along the PT path. So it means that your pressure, which you now measure, might have been affected by the viscous relaxation. So it means that if we are not aware of, or we don't take into account all the limitations of all the methods, no matter what, we can generate the same, for the Raman parameter, we can generate the same error as if we chose a wrong equilibration volume in a phase equilibrium modeling. I could continue on this more, but let's move to the education. I just found this piece of text in the article which was written by Peter for this particular event, and it states that the traditional mineralogy petrology courses have disappeared. I would add that beside, together with losing these observational skills, because those subjects are removed from or disappeared, it's also, at least in Europe, the cases for basic physics, chemistry, and mathematics. So again, we are losing independence probably, because if the next generation is not able to evaluate the observations, and also is not able to critically judge, because they will just use the softwares, the tools which we have, and they will not be able to understand what is on the background, how they can critically evaluate the uncertainties. So this is what was to the curriculum. But we also, in petrology, I think that we have to sell ourselves a bit better, because, as I said, we are material science of the Earth. And I think that if we really implement more physically based research, we can get the interest from also outside geology field, like for instance material science, lithium batteries, and other fields. We can get interest from there. So this goes together with the visibility and bigger picture applications. I go very fast because Sarah is already standing there. So together with the PT estimates, we can invest more into really implementing the mechanics into our interpretations, and we can explore what the open, as I said, the open questions related to the temperature, like heat for the metamorphism, and pressure or stress. And this can not only contribute to better understanding of how subductions are initiated, for instance, or natural hazards like earthquakes, but it can open up our knowledge or our material, studying our like the knowledge which we get from our complex geological material to, for instance, lithium batteries and so on. And on the other side, because we of course study like fluid-rock interactions, and this research, if done combined, it means chemomechanical coupling, reactivity, and so on, we can contribute to societal issues like geothermal energy, CO2 sequestration, and so on. So we have an opportunity to sell ourselves better. So this is my last slide, and where I want to just maybe open up also the discussion, because we have the treasure, we have the observations, and because we are the material scientists of the Earth. And so we may think about to invest more into the basic physics and to get back the independence and make ourselves more important. And I think it goes together with really coming back in certain ways to do basic, which sounds like basic experiments, like to get more internally consistent thermodynamic data, especially, for instance, aqueous species towards high pressure, but we need new kind of diffusion experiments and also non-hydrostatic experiments to evaluate what is the role of pressure and stress on the mineral assemblages. And I said it already 5 times at least, makes ourselves important, and collaboration is important because, you know, we discussed yesterday that petrologists are talented, that even if they are two in one department, they can fight against each other. So we should really put that aside. We don't have to agree scientifically with each other, but we should somehow support, have a vision and support the field altogether. And we can maybe make a use of the technology which we have now and establish, I don't know, because we have 100 years, so I don't know, we can establish virtual research institutions and some educational programs and use the technology for that. Thank you.